Good morning, everyone. Welcome back to the fourth day of Gyan course. We are now ready to begin lecture 8, which will be delivered by our esteemed international faculty member, Professor Sukumar Kamlasadan sir. We are truly honored to have you with us. We look forward to learning from your vast knowledge and experience. Please, sir, the session is over to you.
Okay, so today what we were thinking to have today was to move from what we did yesterday. Yesterday we talked about starting to look into control aspect of electric grid, integrated electric grid, and the control we started connecting the control aspect with respect to the power flow. So the first day we did power flow, then we did the optimal power flow. The goal of the power flow and the optimal power flow will be to, yeah, I'll do that. Goal of the power flow and the optimal power flow will be to give the set of point or reference point for where the power grid operation should have, like in a steady state condition. So you will get the set point or reference point. For example, if you wanted to include integrated TND with IBR, you will be able to get a set point for the operating conditions of inverters or IBR, inverter based resource. What are the set points? Set points can be power. Set point can be the reactive power if needed to go to the inverter and operate the inverter. Mainly the active power is done through power flow, right? Active power requirement for the points that can be derived from power flow. Now, if you wanted to use an optimal power flow, you will be getting the active power considering the cost, whatever the cost objective. So that's what we did in the first. Then what we did was, okay, if I get this number, which is the power that needs to be delivered, can I manage the electric utility grid and managing to deliver the set point basically based on control. So yesterday what we did, we started looking at the power flow, and then we looked at the power flow with respect to time, and then we call it a time series power flow. And we said that using the power flow and time series power flow, how you can derive the stability margin. So I think some of you are not there. So if you will be getting some slide decks in some part. Yes. Okay. And then back in. So yeah. So we also did an assignment on power flow on a distribution network. How many of you have completed the assignment using MATLAB code? Wow, that's interesting. That means you can do the MATLAB code, not here, back at home. So, okay. So if you have completed the assignment with MATLAB, I am thinking that we will do integrated T&D power flow assignment today. Are you up for it? Right? You have two choices: integrated T&D assignment that we can do today, or you can run an assignment to do optimal power flow. Optimal power flow for a 5-node system. I will show a 20-node example, which I've already shown you. Remember the 20-node electric power distribution network optimal power flow example? You can do 5-node. Which one do you want? Which one do you want? Do you want both, or you want integrated power flow or optimal power flow? Both. Very good. Okay. That's the spirit. That's good. So we'll do both today. And then the goal is, after we do both, well, I will also show you some. The next one is probably going to be a little challenging. It looks like you will need to. So if you wanted to run a model of electric grid and then use these set points from generated from power flow and optimal power flow to control devices, you have to develop this model in Simulink and in time domain in Simulink. So I will show you some models which is developed in Simulink with inverter based resources in time domain. If we are really excited, we can do an integrated time domain model of electric grid and the power flow and send the set point signal from MATLAB to Simulink and then use that set point to control the devices in Simulink. That could be nice, if you were to reach there. Let's see how we proceed. So, but what we are going to do today is focusing on power flow, optimal power flow set point. That part is done. We're focusing now on dynamics or changes in the electric distribution grid, how we can manage control devices in electric distribution. And control, we will focus only on controlling inverters, basically, because that is the theme of the game, just the inverter control. We could also control legacy devices like transformer. So I will tell you, I will talk about integrated control with legacy devices, transformer and the inverter without connecting them, meaning just by time scale separation, doing it faster, doing it slow, integrated. So I will talk some theoretical part through slides, and then maybe in the afternoon or some we will show some models. Okay. Now, when you run the models in time domain, you have two different ways that you run. One, you run the models in time domain using Simulink. Another way, you run the models in time domain using in real time, using real time simulating. So there are two different type of real time simulators available in the market. Two companies rather developing real time simulators. Have you heard of real time simulators? Yes, everybody heard of real time. There are two different real time simulator companies running in the market, which are, do you know? And Polarity is people are remembering or seeing, so which means there are Opalati folks around. Opalati and RTDS, real-time digital simulator. Okay. So, in order to run the Opalati system, you need a software from Opalati that needs to be installed, and you will need a hardware of Opalati that you want to run it on Opalati. Running it on Opalati, we call it running it on target. Okay. The good thing about Opalati is that if you run the software, you can use the models in Opalati and run it in your laptop, similarly, not on target. And that is free. You can download it, install it, and then run it on free. Okay. So what that software do? That software will develop models that is real-time like models. Okay. So we'll talk a little bit about that. So just as an introduction. So that's basically our plan for today. So I am going to bridge what we did yesterday and try to connect with you today, because Some of you were not there yesterday, or some of you were there but was not paying attention. So in both ways, we will probably do a catch up. So yesterday we talked about management and control of IBRs. Okay. So what is this now? Well, management control of IBRs again. You say, oh, what is this? Well, we are going to talk about management controls IBR with legacy systems. Okay. What do you mean by legacy system? Do you know the meaning of legacy? Whatever is conventional, which is there for you, that kind of system is what you call it as a legacy. Whatever is so-called smart or so-called newer things that we are adding onto the system, we don't call it legacy. We call it, whatever it is new. So there is a challenge for understanding what is legacy and what is new, and then try to connect it. That's basically the focus. So we'll just do a recap on what we have done last time. So if you were to, and I will focus on controlling the inverter-based resources, specifically on related to power distribution system. So you may ask the question, well, is that the control of inverters or other devices is not applicable for transmission network? It is applicable for transmission network. Because we have distributed energy resources, there are many of those inverters, small ones connected to distribution system. That problem is a little bit more challenging. Rather than having few inverter-based resources which is sitting in transmission network, centrally located, like strong, robust, that problem is a little bit more simpler. So we are trying to talk about problems that are more challenging, which means more exciting. So we are just talking that. That's the reason we are focusing on distribution network. So for a distribution network, intermittent DER output is challenging. That can cause unequal voltage profile. Penetration level can be increased. Voltage profile can be optimally balanced. So that's the thing. So basically, voltage profile is the one what is important to talk about. Voltage at a given node and voltage profile are different. You understand, right? Voltage profile means your voltage at every node. So the every node voltage we have to balance is what we call it profile management. If you are node voltage management, meaning you are taking care of voltage at one specific location. For example, you are looking at a PV curve and looking at what voltage will be on the substation, and you don't worry about it. And we are talking about 24-hour duration. And we are talking about voltage for a particular. That is correct. That is called as voltage voltage profile. You can call it time based voltage profile for a specific node. That is also considered as voltage profile. Yes, you can call that as a voltage profile based on load profile. It's a time based voltage profile for a specific node. That's a very good point. So you have probably 2-3 different degree of freedom there. One is voltage on one node, time dependent voltage profile at that node, then voltage of every node for a specific time, and voltage in every node, the time dependent variations of voltage every node. And so there are, you see, understand, right? So the complexity level increases. Most of the time, people really don't worry about voltage profile for every node, because they assume that voltage profile of one substation node with time dependent, if you manage it, obviously voltages every node can be managed. However, that is not true. The reason why it's not true is because if you have photovoltaic connected at some nodes and it's pushing the power, changing with respect to time, that voltage of that specific node is going to wobble and is going to change with respect to time. So yeah, so when you look at it, the sentences voltage profile, we think that, oh, the problem is very simple, one voltage and then I just fix it. It is not simple. So that's basically time varying management, right, with respect to time and with respect to location. That's what we're talking about. However, there is another part which you need to do, steady state kind of assessment. For example, stability. Remember, we talked about the stability PV curve. That PV curve you have to probably plot with a different load variation with respect to time. So there will be multiple PV curves you may have to plot on the stability property, for example, for entire duration, and then go with the conservative, the worst PV curve condition you have to plot. And then you have problem unbalances, zip load, load variation. So there are these problems are complex, right? There are a lot of things that happens. On top of that, one important thing which you can see, all these problems can be in one bucket called that as voltage management, right? Everything is related to it. So that is one type of problem. So you get voltage. So voltage management, how you do the voltage management? A few different examples I will show, and there will be different ways you can do and multiple things which you can do. So when I show about these examples, you'll get a flavor on how it's been done. Then you can take that up into your thinking table and then try to map it to what extra other things which you can do, like for example research and others. So it's very interesting aspect. You could solve the problem just using that is another area. So very interesting, which I found, that we could solve the problem using things like controllers. That is actually just managing the device with respect to the device capacity. You could solve the problem by introducing new devices, for example, fax devices, or for example, capacitors, or for example, combination, inverters, some new inverters. You also include energy delivering devices like reactors, or not that is passive. Active energy delivering devices like batteries and other devices can also be connected. So the level of management of voltage are different. So I normally call that as like set point control is actually done by controllers. But let's assume that you cannot even reach the set point. Then you need an energy device to reach at the set point. You cannot just do with a controller. Controller will say that, well, I don't have enough ability to control because the set point itself is not reachable. So you need to identify the problem, the type of problem, and then find solutions. So there are multiple different interesting things that you can think if you work through in your mind. So reactive power management is by large important, for example, for the voltage profile. Now the coordination of the reactive power is also important, especially if the reactive power is coming from same location. If the reactive power is coming from few other different locations, coordination is not important. Why it's not important? Because we say that reactive power is not global. It's a sentence which we learn. Why reactive power is not global? Meaning reactive power cannot travel from point A to point B. While in transit, it will be lost either by the inductance, absorbing, or capacitance absorbing. So if you have a node which are three nodes located together, some devices are pumping reactive power on those three nodes, it affects that 3, 4, 5 nodes around it. But it will not affect some nodes in somewhere else. Active power on opposite to that is not like that. If you push active power in one, it goes all the way to wherever it can be reached up to the load, and load draws, except for the active power drop or voltage drop, we call it. Okay, are you following? So, having said that, reactive power coordination is not difficult, because reactive power coordination is only with few devices with respect to the number, but reactive power coordination is difficult with respect to time. So, for example, some are pushing reactive power faster, some are pushing reactive power slower. You have to maintain the time difference or time scale separation. So, coordination is mainly related to time, not related to location, because 3 or 4 devices can be controlled. So, that's something you need to follow. Yes? No? Okay. And the reactive power compensation distribution network leads to reduced network losses, better utilization rate of the power transformer, improves power quality for the users. Because reactive power is directly related to power factor improvement, power quality improvement. So, and then we talked about this. If you wanted to control reactive power control implemented on a device, you could do that centrally, or you could do that locally. Okay, what do you mean by central? Local? Central meaning central substation is I was looking for yesterday. We did a lot of fun with machine learning. We missed. I'll try to do machine learning again. So reactive power management on the DR unit can be local, and that is called decentralized, which means you're having reactive power management at points where it is not related to central substation, and the reactive power management can be coordinated or centralized. So two different way of same with active power too. Centralized control, everybody knows centralized control. Okay, from a central location, command comes, and based on that command, the local devices has to work. Do you? What is the difference between hierarchical control and centralized control? You have a level of hierarchy, which means central will give you something to the like area. Area will give you something to the local, and local will react on it, get the feedback to the area. Area will give feedback to the central. Central will say, "Oh yeah, that is good," or "No, change this." So this is hierarchical. So you are doing in a hierarchy form, right? What do you mean by so this hierarchical form is coordinated because you are coordinating every level of devices in the hierarchical form. What do you mean by local or decentralized? Local or decentralized will say that, well, I don't have an information. You just everything with because of the local, whatever is happening, you exchange the info in the local area, right? If you do a distributed or decentralized local control, you don't need to have any communication or infrastructure information coming from central. You can do take a decision locally. Now, if you take a decision locally, the good news is you don't need a communication network. What's the bad news? Bad news is that you don't get information from the central location what central wants in the local condition. So you make a decision local is good. The decision other local is good. But the central wants, no, I didn't say I want 0, I want 25, but you are doing 0 because you are making sure the local is good. Then you have a challenge. Then you don't know that knowledge. You don't have that knowledge. So local controls are generally considered as delta controls, which means you don't look at 25, you make 25 to 0 and then you get decision on it. And then remaining whatever is required to be taken by some devices at a central location, then manage that. So these are some of the, but there is an extended good news is no communication network. Communication network on a power distribution system is not generally implemented, so it's a little challenge, right? So, high communication cost. So what I'm going to show you is how you do the control. So for the control, what we are talking about is not the control of the inverter. Okay, now you're talking about control level. So control comes in different level. One level is a device level control, where the device controller will work on the device to take care of the objective of the device. For example, for the inverter, one device level control is to maintain the voltage of the PCC, or heard of PCC, right? PCC is the point of common connection or point of common coupling. So inverter will look at the point where it is connected. It will maintain the voltage at that point clean, depending upon whatever the power is pushed from them. That's the device level, one objective of the device level. Second objective of the device level control is to make sure the active reactive power transfer is taken care of. Whatever the reference for the reactive power, whatever the reference for the active power is taken care of. Today afternoon or maybe tomorrow, I want to get inside the power electronics in the inverter and then show you only the control architecture of the inverter as like kind of a grand conclusion about this. Because of the electric grid thing, we are still on that. So that's device level control, local level control. The next level, we call it secondary level control. Secondary level control, what it does is the area where you have will provide signal to this local control and say, hey, this is the signal that we want. To derive that signal, you need some control action. That's some controller. What are the signals that is important from the area which goes to the local device? Voltage and frequency. These are the signals that is basically required to be going to the local controller. So that's why we call it secondary level controller. Then you have what we call a tertiary level controller, which comes into the substation and the substation management related to that. So there are three levels of hierarchy that is there in the management. So what we are talking today is not a local level, device level control. Assuming that inverter and the battery or whatever is required can take care of whatever set point which we are going to give, we are going to give that on secondary level. How do we manage the secondary level coordinate? That's what the topic. Then we will be slowly going inside the box and see how the box really. Oh, to do the secondary level control management and secondary level control testing, you need the local control. So you have to put a naive or baseline local control inside the inverter, a generic controller, a generic inverter architecture we have to put for testing purposes. So for new model. So I'll show you how that is done in a generic inverter, then we can work on that on the other. So having said that, if we were to do, I'll show you the block diagram. So if you were to do, for example, control a multiple inverters, 3 of them, DERs call it, and DERs are but it's all inverter there, right? Because of reactive power. If you want to control multiple inverter, what you have to do is you have to look at a target node. So we are now looking at a voltage on a one node for voltage, changing with respect to time. So that node voltage can be constant voltage or changing with respect to time. So we are talking about changing with respect to time for one node. This also we can call this as a profile. So you have a target node and a measured node at that position, and then you are changing this delta V, you are giving that to a control architecture. And the output of the control architecture is a reference set point or Q going to the inverter. And what the inverter does? Inverter pushes that reference. Now, inverter control sits inside this, which is a local controller. Now we are saying that that local controller is doing a good job, inverter has capacity. So we are actually wanting to just derive this reference. Good? Following so far? So where is this inverter? These inverters are located in some places. Where are these a target node? Target node may be in another place. These target node, where is a reference node? Reference node you create, or it can be another place. So that and a controller may be sitting on it. So this delta V will be using some communication infrastructure to do this control architecture, and that set point will be going through some communication infrastructure to the inverter if you are using a COM, infrastructure. Otherwise, you have to do some local management for that. Following so far? So I'll show you, for example, this we talked about. So here is the 3 inverters, and you are looking at a node of interest here, right? Which means this, I think we already talked about from here to here the voltage drops. Remember, the voltage is going down. So you are not looking at here. You are looking somewhere here, something like that you can target, right? And you are using these 3 inverters basically to take care of this, assuming that they are like nearby, physically looking at the picture. We were talking about it, is this picture really nearby, or that's a different question. You got to look at that and do that. Now, there is a legacy device sitting here. What is this? What is this toy? What is this box? Voltage regulator. The voltage regulator is sitting here. So if this voltage is low, this voltage regulator will feel the voltage here. This voltage regulator only looks at this point and this point. Remember that? I told you, we will not look at any. So if this voltage is low, this voltage regulator will tap. And if we have a DER here, DER also will push reactive power. That is coordination. Now you need to make sure that these two has to be working together. Otherwise, you have a problem. So this, how the coordination can be done? In the inverter sense, it is not difficult because this works very fast. Reactive power, this is like 80 seconds. Remember 70-80 seconds we talked about. So there is a time scale separation, because if you take care of the time scale separation, meaning through, for example, Nyquist or some other, like 80 seconds, if you have 80 divided by 10, between 7 seconds the inverter is pushing the reactive power, then we are safe. We have a time scale separation. Then you don't need to do any communication device and connect and things like that. So having said that, these 3 DER is basically be controlled. Now that controller box may be sitting here. or maybe sitting in a house right here. We don't know, but you have to send signal from the controller, and the controller box has to take a voltage point from here at that point, whether it is through communication or something else. You got it, right? This is basically the management. Okay. Now I'm going to talk about one method which we implemented. There are several methods that can be implemented. This method is a classical method, which is nothing. Well, the integrated part is new, individual part is not new. So, for example, this control is done through a classical method called LQR. Have you heard of LQR controller? LQR is controller is coming into a group of control methodology called optimal control. Okay. Have you, I think there is a course here on optimal control, definitely. Maybe on the master's level or something like that. Optimal control, is a class of control, okay? And what is optimal control? Optimal control is deriving control signal using optimization. We know optimization. We know. We already learned optimization a little bit for optimal power flow. So, optimal control, what it really does is it looks at a objective function and some of that objective function, and you minimize. Okay. Now I'll tell you what is this objective function. This objective function as x transpose x. What is x transpose x? What is x? State variable. So you got x, state variable, you bring x transpose x, square of x transpose, and you multiply that with a number q. Okay, that q is a magic number that you can derive to do whatever you want. Okay, so that's a knob. Then you have u r u. What is u? The control input which is going into the control. So what your goal is to minimize this state's error. So basically this is done with the delta x, minimize the state error dynamics, and also minimize the effort that you put, which is control. So control output that is going there, I want to make sure my effort is very low, which means lowest cost that you want to keep. So that is the optimization. Okay. Oh, so you say that's optimization. Why you are calling optimal control? You are also optimizing the control variable. Yes, in general it is called that. No rocket science. Very simple, right? So optimal control is basically this. Now, if you have this optimal control, this is quadratic in nature. You see? Oh, there is no solution, closed loop form. So you can do some solution. There are some math. There is something called Riccati equation, algebraic Riccati equation. These are some of the mathematical things which is already been done. Nothing new. I mean, what I'm saying, so already been done. You can utilize the classical form of that, and this you can take a first derivative of this. Oh, remember that second order equation? If you take a first derivative, you become a linear equation, and equate that to zero. Remember the convex function? We said same idea. Just go derivative and equate that to zero. Then you will get your equation in closed loop form. So that's basically the equation in closed loop form. Now, if you get that equation in closed loop form, you can get the feedback gain out of that equation, and that gain you multiply with the state variable, you get the controller. This type of controller is called linear quadratic regulator. Optimal control, yes. This form of optimal control is called linear quadratic regulator, or LQR. Why it is linear quadratic? You already know. It's a quadratic function. You are linearizing, so it's called LQ. What is regulator means? We are putting this to a step regulation. I think we talked about the difference between regulation and tracking and all that, So what is regulation? Water tank, set point change, that's regulation. Not a tracking. You're not doing tracking. You cannot do tracking with this type of control. It's just only regulation. So it's called LQR. So that's basically the regulation, and you can actually calculate this variable for the noise. Okay. So that is this by regulator. So if you are going to derive measurements, you have a challenge that you have to get the state variable to do this control. Okay, this is called state feedback control. It's a classical form of control architecture that you call state feedback control. What do you mean by why you are saying? So that means there is a controller which is not state feedback control. Yes, there is a controller. Almost all the controls are not state feedback control. What is the type of controller that you do which is not state feedback? It's called output feedback control, not state feedback control. Okay, so you measure an output and then you use that as a feedback. You know feedback control, right? Feedback control concept, everybody know. Feedback means you get an error, then you do it. Feedback control you do while you're driving too. You adjust with your eye as an error, then you know that's feedback. You close your eyes and drive is open loop control or no feedback control, which is not possible. It's difficult, right? So that's feedback. I'm just giving you a conceptual idea. Otherwise, it's so output feedback meaning you take the output and then feedback in. Output feedback controls are most of the controls are that. Why? Because getting an output is easy. You put a sensor, you collect the output, there will be some noise. You put a low pass filter or some light filter on the sensor and you collect it and then you do your job. Output feedback. State feedback control is not easy. Why? Because states can be, states are actually mathematical, write equations and you get states can be physical or non-physical. So for example, your output is an acceleration. Your states are position and velocity. Your states are physical. I can get position, I can get velocity. What happens to your state is velocity square plus position square divided by 36 order square root of that. I don't know what that is. That is actually a mathematical term. So states can be challenging because states can be physical or non-physical. Understood, right? Now then why states? Why do you need these states? Well, these states are the one which is affecting the output. To complicate things more, many states make influence output, may not influence output. Some states may influence, some states may. So your challenge is not just get the states. Your challenge is also get the states that is required for you to get influence output. So state feedback control has these kind of challenges. So normally what you do something called state prediction. Okay? State prediction is done by a class of don't want to digress into control theory, but their state prediction is done by a class of things called observers. Okay, observers or state observers we call it. Okay, states are generally called not called as parameter. It is called as observers, variables. Okay, so you observe the state. So state observers are coming in different form. Classically, is written linear observer, LM, Lavender Market observer, non-linear observer, predictor observer, current observer. So you can observe one step ahead, you can observe one step behind, like wonderful story there. There are observers noted in the form coming from filtered on communication network, and one of the classical way of observing is through something called Kalman filter. Okay, so Kalman filter is defined by Professor Kalman and in one of his seminal work, and he came up with this what you call it as a Kalman filter. It is ideally used for filtering purpose, but it can also be derived to use for observing. So I am not going to go in the detail. So there can be a box to do state estimation. You understand the purpose why we do state estimation, because it's state. So with this, you can do the control architecture. So that control architecture is represented in here. Okay. To do the control architecture, you need the electric grid model. Otherwise, you cannot do the control. Right? Electric grid model. Oh, by the way, you see this right here? This point, and this is basically the control area. So you need an electric grid model. How do you control without an electric grid model? How do you get an electric grid model? Well, if it is a steady state electric grid model, you can pick it from your power flow. Remember, we have a power flow model ready. So if this model is changing, you cannot pick it from the power flow. Okay? What you do? You have to take the power flow models and find out what will be the impedance of the electric grid when the voltages and current changes. Okay? Such impedances representation of looking at the voltage and current can be done through what we call Thevenin impedance. Okay, what do you mean by Thevenin impedance? You're looking at a point right here and observing the voltage and current. From the voltage and current, deriving an impedance, which is a fictitious impedance, not the impedance of the line, but the impedance seen at a specific point of time. Okay, so having said that, uh, you can actually develop that, and you normally develop these impedances through transfer functions. Okay, why you impedance derived through transfer functions? Because if you derive a transfer function representation, you can get this fictitious impedance which is changing with respect to time, because transfer function has a property of frequency response or frequency changes. So you can actually have a impedance derived through transfer function. So what we are doing here is we are trying to get the impedance. We are trying to get the impedance for so when you get the impedance, you have to get a relationship. So right now you are looking at relationship with voltage and the reactive power, and you are getting the impedance through voltage reactive power combination. Okay. So after you get that impedance, you can put that impedance in the form of a optimization algorithm, and that impedances from the optimization algorithm can be represented in the form of a transfer function, and that transfer function will be an algebraic representation. That algebraic representation can be used to derive the state space for your control. Remember that for your, well, I think we talked about it, I guess. For any controller, you need a state space representation, right? X dot equal to Ax plus Bu. So you can get this X dot equal to Ax plus Bu form with the help of this. So what we are doing is this part is a transfer function estimation, and this part is developing the state space, and then we'll pass it to this controller, and the controller will do. I just storyboarded it. I will not, the next level is showing you the code, which I will show you code, but to get to the code level, you need a little bit of hands-on and work on it. Are you following these steps, or are you understanding what piece is what? Yes. How many of you are understanding what piece are? Raise your hand, please. Yeah. If you understand this better, the third semester it will be good for you. I know these people are like undergrad, right? So they are still having challenge. Okay. So that being said, we will look at some examples. So here is a remote node, 107 is a node of interest, and we wanted to maintain the voltage in the node of interest 1 per unit. Now what happens is we are seeing there is a step change in the power, so the voltage is dropping. Now when the voltage is dropping, when the voltage is actually at this time when it is dropped, we are actually putting the reactive power, and we are trying to improve the voltage back to 1. So there the pink one is without a control, this line, and this line ideally should be a straight line. There will be some dip there, it should be a straight line. So now you see this is the response time of the controller with communication closed loop, and this is how the output affects. So basically it's not, it's good, but it can be more perfect. What happens to the taps? If you look at the taps in tap operation of the regulator, you see the after the taps are done, the voltage after this, when the load varies, the taps are done, the voltage is changing. So when voltage is changing and going up and then going down, and these are actually for tap A, tap B, and tap C. Oh, you understand tap, right? The transformer there is working, not to maintain the tap. Now you can see that the with the DER, reactive power inclusion, you can actually avoid the, you don't have a tap operation. This is another example where target voltage is higher than the reference voltage, leading to negative delta. So you are putting a reactive power to make the voltage close to 1. So this is a delta V, and then you are putting the reactive power reference. So reactive power is changing. So you see that when the load changes, the voltage delta is has to maintain 0. So you see right here, they are changing, but the voltage is kept, deviation is kept as 0. So if you look at the taps, this is actually the taps, the pink one. Now when with the controller, you see these taps going up, and then it come no taps right here. These taps are avoided, and there is much no taps in here. And then you see one change in here and one change in here instead of all these change. No coordination, but with time scale separation. You understand this graph? Makes sense, right? So that's a coordination with respect to the device. Yeah, so this is a type of voltage reference tracking. Here a remote node is chosen. Load change at 2, 6, 9, 13 seconds. This is basically to profile. So when the time changes in that specific node, the the uh, the voltage changes. At 8 seconds, the reference voltage is changed from 1 to 1.01 per unit. So somewhere around here at this point, reference voltage is changing from 1 to 1.01 per unit. And you can see that all the time, except for this time, the voltage's error is pretty much maintained constant. That spike is because it's a reaction, the time. So you see, and just spikes. Ideally, that's what we wanted. So, by the way, you see right here, this is the time in which the initial time for ADMM loop to be closed. So it's not doing anything here. It's doing only after that. So which means there is a time at which there is a response for the controller. Then only it will react. That's another thing which we can see from here. So and that the last one is I think probably this is the last one. At 7 seconds, one of the DER is out. So there are 3 DERs which we have. One of the DER is out. Now you can see that the loss of DER at 7 seconds, there will be one DER lost right here. So you can see this Q2, QCC, that DER is basically the reactive power going back to 0, which means that guy is off. It's gone. There's nothing, it's going out. So that is going out means what? The other 2 DER has to maintain the voltage. So at 7 seconds, that DER is going out. It goes like this. And then your other 2 DER is maintaining. The loss of DER is happening right here. Another 2 DER is maintaining. And you can see that it is maintaining still the voltage profile because the inverter has extra capacity or extra juice on that DER. And that power from the DER is, active power from the DER is very low. If that is not happening, obviously it is going to fail. So the DER, losing the DER can be for any purpose. So if you are actually having a DER and then it has gone to maintenance or it shut down, it's not responding. That also one of the reasons for this. Okay, so that is one. Any questions on this? Yes. Is 66 closer to 107 or not? Is that what? Yes. If you are controlling 66 instead of this 107, right? Ah, yes. Oh, legacy, only legacy. So 66, if you look at 66, very interesting question. Not 3, 4, right? 4, all 4 should. No, no, no. Oh, the only regulator you're talking about. So 60, so very simple. 66 is right this, right? Connected to this. That is on the source side of this regulator. Whatever is on the source side of this regulator will not see. So that regulator is not visible. So this is a very important thing. I think I have a graph which photovoltaic connected. This regulator get messed up because regulator see on the load side and there is a voltage drop, regulator taps up. So the voltage drop happens when the load is there. Let's assume you have a photovoltaic there. The load is changing, but perceived load is PV is pushing to that load, which means the regulator will see a light load. When the regulator sees the light load, it will not tap. It may be tapping down instead of tapping up. But photovoltaics is delivering the power. If you tap up, what happens? The voltage goes up instead of going down. Which means, and then if it goes up, then the regulator will see even lighter load. So it taps up again. Finally, it taps up, and then go to positive feedback, and it goes to the infinite. So that also can happen. But anyway, so this one right here, it will not do anything. Now let's look at this. You can actually do look at it. If this regulator is sitting there and looking at this point, this regulator is on the back of this, and nothing will shift. So look at this regulator. This regulator is looking at there, it's sitting on the back, it will not sit. Only this OLTC will be. That's how the regulator works. All the time, everywhere you have a lateral. So this is put here just to take care of this one. Because that ones are actually messing up. The voltage may be very low. This is put here just to take care of this area. Maybe something. And actually that node. Maybe it's affecting this area. So that's what. And this one is putting here is just because of that. So that's how regulators are placed. It's actually placed practically. So there was a question which was asked by us when we tried to implement it at the utility. Oh, these things are wonderful in here. In the field, where will you put this? This is, how do you control? Which point you control? There are several nodes you want to control. And you think that yours is a wonderful thing, everything will work, but it will happen. Give me simple solution. There is a trick. The trick is these regulators are placed by the utility based on the experience. Some of them is even rule of thumb, no math involved, just looking at the utility where the voltages are collapsing. So what is an indication? Those nodes are a good indicators that where you put some devices because they are the one who is working. So we said that, well, let's pick the worst one and then put one small battery there and just control that battery. So we were talking about which one, you were asking which one you should control, how many you control. It's very complex. So we call it controllable asset. So you only control that specific part. That is how you do it. But I think I hope I answered your question. So what happens is, if anything happens like that, and none of them sees at 66, and 66 is going down, you could have 2-3 PVs there to take care of 66 if there are some points that we still. Okay. Other questions? All right. So now what we do is we try to look into what you can do with energy storage. So there was a big discussion yesterday. We talked about you can do inverters for reactive power support. You can actually use energy storage for active power support. Right? Oh, inverters cannot do active power support. Inverters with photovoltaics also cannot do active power support because photovoltaics will be asked to push the power maximum to the electric grid. If you ask the photovoltaic to manage the power, then you call it curtailing. Then you say, I don't want to curtail, I don't want to manage. So who does the job of active power balance? Only a device that can be controlled can do the job of active power balance, and one of the devices is battery energy storage. It could be any energy storage we talked about. It could be small pump hydro. It could be some, any energy storage can be used there. That energy storage that you are connecting along with coexisting with photovoltaics, we make that combination dispatchable. And we talked about the meaning of dispatchable. What do you mean by dispatchable? So how do you connect the energy storage with the photovoltaics? You can have, I think we talked about it yesterday, I'm repeating it one more time. You can have an energy storage and the PV connect on a DC bus and have one inverter, smart inverter. You have an energy storage and you can have a PV, multiple of them connected to DC bus. At the end, you connect one energy storage again on the DC bus and then convert it to AC. You can have a bunch of photovoltaics in one area doing whatever it wants to do, and in one bus, I'll connect an energy storage. So two inverters, one inverter is for the entire PV farm, another inverter for the energy storage, and that energy storage and inverter I control. I don't manage any of the PV. I just leave the PV, whatever it can be done. So when we were implementing this in the utility, we divide them into controllable asset and uncontrollable asset. Uncontrollable assets are the one which change it, do whatever it wants, like photovoltaics. Controllable assets are considered as battery energy storage. And then you manage the control apps. So this is a application for a battery energy storage. You have applications in battery energy storage, the transmission network called frequency regulation, T&D upgrade deferral, spinning reserve, flexible peaking source. These applications are generally considered as auxiliary service. You heard this term? Have you heard this term? I think we mentioned this yesterday. Auxiliary services are support services that you do with the device for the utility. One of the auxiliary service is spinning reserve. Spinning reserve meaning you keep the reserve for the generator and then utilize for. That's an auxiliary service. Why it is called auxiliary? Because that improves the grid stability and reliability. Whatever way it is, it's reactive power improvement, frequency stabilization, angle stabilization, power stabilization. All those things are considered as auxiliary service. In the US or in any place, I think for that matter, battery energy storage has only one benefit, which is to regulate the frequency or active power regulation. That's the only money that you can get, because that's the only market that is monetarily taken care, and that call it capacity markets or active power market. So having said that, frequency regulation is done in the transmission level. Unfortunately, frequency regulation is not done in the distribution level. You can do frequency regulation at the distribution level by pushing the power from the battery, which is set by the substation. So how much frequency I need to regulate, I convert that into active power, and then I will give that number from the management system to the substation. Hey, I don't need this. I need this and this to give the power to maintain the frequency regulations. That signal I keep changing like a tracking signal. And that signal I will, with hierarchical control, I distribute to the battery and say, battery, can you supply the signal? So it takes care of the photovoltaic changes, and on top of that, it takes care of the auxiliary service. So that's the way you can actually give benefit. Other than that, you can do voltage regulation, micro reverse power flow conditions. These are some of the things which you have not discussed, but you will interconnection related aspect, voltage balancing, these things. Oh, by the way, if you are going to get the reactive power from the inverter, you cannot get the reactive power from the inverter without some active power source. So this is something which is, for some people, is kind of unknown. You may think that reactive power is free from the inverter. Connect the inverter. No, you need some active power because of the losses and other things which is like. So we have 250 kW in battery and 1 MVA inverter. If we want to deliver 500 kWh from the inverter, which is half of the capacity, we said that we need around 80 kW active powers from the battery. Then only you can actually do 500 kWh in power coming from the inverter. And where is that 80 power goes? It goes to internally to take care of that. So reactive power support also need some little bit level of active power contribution from the source. But you cannot get it from capacitor. You can. It is high. It is high. That is what I was, we were saying. That's actually almost 10%, 20%, 30% of the capacity. You are actually. I mean, these are some examples. Sometimes you may be able to reduce that. So you consider that many of our modeling, especially on the electric grid side, I don't know. I'm not expert in. Don't consider myself an expert in power electronics, but in the electric grid side, we always say that switch losses is negligible. You don't. These are the kind of things which you do, and then you model it. But from this, and much of it is not going to the switches, by the way. It is all going to these big filters that probably is sitting there. The inductors basically, is the one which is especially AC side. DC side is a capacitor, not much of a problem on the DC end. AC side filters takes a bulk of this thing. And AC side filter management also is now getting more difficult because of power quality issues. So L filter is now going to LC, now it's LCL. There are combinations of filter, and the topology is different. Again, the filter pattern is just different. So it's not small. So the point is that active power coming out from the back end is a requirement for just not from the on the reactive power. With that being said, so what we have done is we have included a battery energy storage that can do multiple functions of the distribution system. Renewables firming. Have you heard this term, renewables firming? Renewables firming is changing of the intermittent renewable to flatline. This is renewable firming. Okay. Renewable firming can also be considered as smoothing. Smoothing the output from the renewables. But you don't call it smoothing. You can see that as a firming. Energy time shift. You know what energy time shift means? Yes? No? Have you heard of energy arbitrage? Energy time shift? No. You know what it does? It actually takes the available power of the photovoltaic, store it in the battery, and when the photovoltaics are not there, push that power from the battery at a different time. That's called energy time shift. Voltage support, we already know what voltage support. So for voltage support, you need reactive power. For renewable capacity firming and the energy time shift, you need active power. So the battery can be, along with the inverter, can do both the job. So energy time shift and PV smoothing, active power, voltage support and volt var coordination are different things. No, do you want me to explain a little bit? Okay. Voltage support means you are actually making the voltage at a point and maintaining that voltage constant. That's what we just explained in the previous slide. For maintaining the voltage constant, you need reactive power. But that reactive power that you are supplying is is changing. What is important is to maintain the voltage constant. Okay, this is called voltage support. So what will be the output of the output reactive power from the inverter at that time? Some number. It's changing all the time. Changing. You don't care about that number. It is reactive power support, as opposed to the voltage, is based on pushing a set reactive power from the inverter. So I will say that I need a 50 kW. I will have to put 50. So my controller is signal is reactive power, controlling reactive power, not voltage. So I'll be getting 50 kW. Now let's assume that I want a reactive power and voltage control. I'll be doing 50 kW plus that waveform. So the waveform for the voltage, let's assume that it is something changing. You will be seeing the reactive power also. So you will be seeing, so this will be the reactive power. This is voltage control, right? If I want a 50 kW reactive power, I'll be getting same waveform shifted up because you have a reactive power on top of it. I could have drawn a better waveform, but I mean, you understood the idea. So having said that that is another way that you can to do reactive power. Now let me ask you, what is a volt to hour control? You are controlling you're controlling the voltage profile based on a curve for the reactive power for the voltage to maintain the voltage with respect to time. So you don't have a constant voltage, you have a changing voltage that is 0.9195, and you push reactive power for that specific voltage and change that. That's called volt to hour control. Okay. There is also something called volt to hour watt control. Volt to hour watt control is you are actually doing volt to hour and then you are also doing watt. Watt means the active power coming from. Okay. So this volt to hour regulation and volt to hour controls are actually mandated by the utility, and there is a standard curve that you have to follow, and the inverter follows that. So smart inverter has volt to hour control capability. You can push the button and this inverter will do volt to hour control capability. It's possible. So here is an algorithm. We are not talking about that algorithm, but so what we have done is we did this implement. Oh, by the way, this is implemented in the field and it's fleet-wide adopted. We gave the licensing, everything to the utility. So this algorithm, which is all through all four of them, is modeled for a utility scale inverter and modeled in the lab with real-time control sensing. And then from the lab, this is our lab, we send that set point signal to the utility in the field. This is a 1 megawatt site, and this is the battery energy storage. So this is actually 250 kW 3-hour battery energy storage. It's a 50 to 50 feet long truck if you look at the battery energy storage. So that is co-located with this. So you kind of supply that, and once you supply that, you will be able to. Once you supply that, you will be able to do the energy arbitrage where this power is used in here. You see, this is night time, that is a daytime. So night time the power is pushed. This is the state of charge of the battery. This is smoothing. So, oh, by the way, battery cannot do flat line for the photovoltaic. It can only smooth the intermittence. So the goal is basically to make the power output from the photovoltaic which is, let's assume this is the photovoltaic. The goal is to make the power output okay. We are not making flat line, right? If you do this, the goal is that you can, this is called smoothing, okay, or this can also be called as firming. Okay? So in here you see this black line is a smooth line as much as it can, not very smooth, but best smooth line as opposed to this red line, and this is the arbitrage point. So our utility wanted to have a smooth line without the forecast, energy forecast. So we are smoothing. Oh, so time limit is 1 day. So this is night. This is 9 o'clock, and this goes back here. This is so. So after we implemented, we were monitoring it every day. There are several other figures. I think you can use some of these papers to look at it. We did combine all three and then check it. So basically, if you do that, you see that distributed energy resource, this is solar, this energy storage connected to loads and capacity. You can actually use this resource controller to control in the field as opposed to the other theory. So you can actually manage the electrical control. And this is generally called, I think there's a term here, and I started seeing when I was in IISc and all that. This is generally called power plant control. So in India, there are a lot of people now talking about power plant control, and And the power plant controller is basically this control that is actually below the management system of the utility, locally taking care of the PV farm output as collective PV farm output. We talk a little bit of the extension to volt or watt. So this is actually a feeder. It's also a real life feeder. This feeder is in North Carolina. This has 8,500 node in that feeder. This is the OLTC, and these are regulators, 3 of them, and this is our laterals. And we are looking at 2 energy storage locations. And you may see that these locations are, I told you the trick, along with that. And these locations are used for volt-var control. So when we do the volt-var controller, we are looking at the voltage profile and making sure that voltage profile within the band. And we are also looking at the step change in the transformer taps. So this is without control, this is with control. So you'll see the taps are shifted. That's one observation. Second observation, some of the taps are not happening. So that is another aspect. So you have 3 scenarios here conducted for voltage, and now this is a voltage wave profile with respect to time. So we talked about one location with respect to time, and that's basically your time management. And the evaluation metrics. The last part is the metric part in here. So this is the regulator taps, total taps, and every scenario we are looking at how much taps are reduced. So you see the reduction in the taps, 37, 49, 20. This taps goes up, but when you do both of them, volt, var, watt control, the taps goes down. So this is basically a comparison of what taps happens with respect to each of those. So volt, var, volt, watt control cannot reduce the tap. You need var. So if you do volt, var control, it reduces the tap. But if you do volt, var, watt control, it won't reduce from there much, but it reduces at least 1 or 2 taps basically as an indicator. And then you can also do something called ramp rate improvement and power loss improvement. Ramp rate is something that is, everybody know what a ramp rate is? No. Ramp rate? No? Okay. You know ramp? Ramp is changing in ramp. Ramp rate is how fast you ramp up and how fast you ramp down. Okay. Now, what is the importance of ramp rate? Ramp rate is the one which controls how fast and how slow you respond to the changes. So, for synchronous generator, ramp rates for controlling, pushing the power from synchronous generator to the output is around 2 seconds, 3 seconds, including all the loops connected with that. So, that's basically including the ramp rate of the synchronous generator. The photovoltaics and other devices, the ramp rate is even faster. It's very fast, it goes down. So the ramp rate actually is something which is happening for different ramp rate. So one generator, another generator, photovoltaic, having different ramp rate. This is a challenge for the utility. This is directly proportional to how you can manage when there is a power slump happens. So let's assume that there is a load and this load is lifted, high load change. How fast the generator changes to support that load is important. All the generators together. If they are not changing fast to support the load, then the protective systems will activate and then it will get rid of those generators. And if it gets rid of the generator, then you have cascading. There are load more, generator less, generator less. So with the renewables, the challenge is renewables when you have, I think I have probably a graph here. No, I think I have it. Renewables when you have the renewables create in general a shape much like this. Right? So when you create the shape like this, On the flip side, renewable will have, when you look at the power graph, output power graph with respect to along with the renewables, with respect to time, E, all resources with PV, the power graph in a load change graph will look like this. Why? Because at, for example, 9 o'clock or something like that, the renewable power is pushed. So the other generator power will start swinging, is going down like this. And this is generally known as duck curve, because this is more like a shape of belly of a duck. It's going down. And so if you look at this, this is like a duck. So this duck curve is something that happens in the power grid if you have more photovoltaics connected. Okay. Now, if you have this and you are actually trying to lift a load and there is a load change that happens at this point, you will need to work against normal operation to satisfy the load. On top of that, with the PV, because you are dipping, because going down because of that load, right? So what you have to do? You have to have somebody who actually ramps really fast at this point. If you don't ramp really fast, then you're out. Okay? So utility, what is the normally is use hydropower plants, peaking power plants, and fast gas turbine plants to ramp up to that fast. Okay, so this is the ramp rate problem or ramping up problem. So what you have to do for that is you have to make sure that these devices can move fast to control this duck curve. Are you following? Okay. So this is done by other generation plants. So cycling plants, we call it, which is plants that are running with steam generation. Cycling plants, there is what we call it as cycling time, and you cannot ramp up that fast during the cycling time. So you need to have other type of plants which are not cycling to take care of this. This problem is generally called resource mix allocation or resource diversity allocation. So you can only survive in some condition if you have hydro, sometimes wind, sometimes battery energy storage, hydro peaking as a mix. Just having PV and nothing else, 100% renewable target, you go. You cannot operate the electric, you collapse. So there is people who are, if you look at the literature and if you search on Google, there are studies done for, you just Google and search on duck curve studies, you will see some, writing reports on duck curves, challenges of duck curves, you will see resource mix allocations, you can search with those keywords, resource allocation. So you will see a lot of work done. I'm not asking about, so when you search it, so this is what I do. When I want to learn something, I don't search for technical papers. I search for industry reports and electric grid reports. That gives you a sense of the type of the problem that is faced, challenges faced in the real world. Then you can come back and look at whatever. So when you search for it, do not search for, my point is that do not search for, you can, but do not just get biased into IEEE papers and other papers. And there, some of them are already based on the real life, but there are a lot of reports which is being working on. So the two problems on resource mix, like ramp rate, and the voltage problem that we face, these are the two main challenges faced by renewable integration as of today. So this voltage not being controlled by renewable and not being supported by renewable inverters for reactive and active power, active voltage is also one of the reasons that we saw a big outage in Central Europe, in Spain, like 1.5 months, 2 months ago, there was an outage in Spain, which was interconnected to France. And that is, there's a report coming out, not fully published, and things like that. That was because IBRs connected to the electric grid at that time actually is doing constant power factor, no voltage control, and the voltage changed dynamically, and the interconnection grid tripped. So there are instances that is related to these two problems. Having said that, do you understand the ramp rate part there now? So looking at that, you can actually see ramp rate improvement with this what, how much percentage of the ramp rates are improved in each location. So for example, you can look at the ramp rate improvement in here, in here, in here. In so one of these work, what we try to do was, you make this duck curve is in the generating station, by the way, because generators see the duck curve. So we thought of an idea, can we make that, so this duck curve is coming from all the renewables coming in there. Can you make this duck curve local? So we kind of call as a local duck curve. So many of these small duck curves add to this big one which is seen by the generator. So the idea here was, if you have a local duck curve, you capture that ramp at that local place itself. Why you want to capture it at the end when it becomes a big duck part there? So these areas you can localize, and you can call these battery and storage sweeping guard, and then try to take care of the ramp rate locally. So that is one. And I think we have maybe some time. So you can now make this management architecture for multiple batteries and multiple PVs. So this architecture is also implemented as a tool. This is how the power grid operates. And this power grid management system on a distribution system is called DMS. Have you heard of this term? DMS, distribution management system. So the DMS actually do power flow, load forecasting, feeder reconfiguration, capacitor improvement, OMS, outage management system, fault management. These are the kind of things which are DMS. And for renewables, there is also a grouping of renewables with respect to some standards and guidelines. For the electric distribution system, the standard used by the operator is IEEE standard. IEEE 1547 or 1547 is a standard mandated by the renewables. What we were doing was, we were actually supporting these DERMS with the architecture that can be used to control multiple renewables and multiple batteries. So this was funded by DOE. There is a website here you can actually look at. There are some only odd people working on it. So worked on it rather. I closed the project in 23. So that is one thing that we were doing. So what we did was, we were actually developing a tool, and that tool is this. And that tool actually communicate with the real feeder, and data is transferred through Python scripting to deliver the set points. What is that communication? Same thing, hierarchical. Take the feedback from the local, go to the central substation, then you make it into area, give the signals to the area, and from the area, give the signal to individual local DVR. Okay? This whole process is done with respect to time, fictitiously, meaning not changing anything in real. After the set point is given, that is the DVR will be changed. Until then, it is all managed using power flow. Every 10-15 minutes power flow data that we calculate, and then you run it. That's basically the architecture. So for doing all these things, you need a tool, right? I mean, you need to coordinate with multiple devices, and that is what the software is trying to do. So you can, with this tool, look at the areas where the voltage profile. You can also look at the area where there is a load generation balance. So you can actually look at this local duck. So why is this duck curve happening? Because generation is high and load is low, and then it's changing. So with the battery and PV and load, can you make this flat line? That is local, small group. If you make it flat line, there will not be power exchange. I think we were discussing yesterday. There is no power exchange between this group to the other group. If there is no power exchange between this group and our group, I can make this as one group. So now I flip it back. I look at where is the power exchange. The point there is no power exchange, I take them and make a groups with respect to time. They're fictitious groups. There's no control there. And that group I color code and I say, okay, 20 of them can work together. That will make the power balance. Then I send the signal to battery, group of battery or whatever to that point to control so that the power is balanced. And I continuously do that every 5 minutes, every 10 minutes, depending upon, whenever you want to do in your system. So if I do that, I can look at each group with the varying PV and varying load. I can look at each group and see the output coming from the group and the set that I am giving to the group are same or not. So this is actually this orange and the blue should be on top of each other. If they are on top of each other, I can say at the end at the substation I get a flat line without having this duck curve. So you see this has to be like a zero, like a flat line. If it is like a zero and flat line, these changes are not there, then I am good. But you still see changes here. Why those changes are there? Because I don't have enough capacity to make the photovoltaic output constant with the battery. So you have a choice whether I put more money to put a battery to make it flat line, or this small change is okay. I leave it like that, and so the tool will give you with the current scenario what best I can do. I can use 1 battery, 3 battery, 100 battery, depending upon that. So I'll give you different options so you see that, and then you can also give the output set point coming out after you control, before you control, and the changes. And these are like a reactive power. Oh, this is another interesting thing. Here, instead of a constant number, we are asking the distribution network to follow a pattern. Right? This can be ancillary service. So I am not asking the distribution network for a flat line. I'm asking flat line is good, but on top of that, give me this shape. That shape is supporting for the frequency or some other. And you can see that that shape is honored, but in some places that is not honored. You see, it's going up. But with the controller, this blue dot is without. With the controller, you are actually able to go closely track that. Yes. So this case came up yesterday. I think we were discussing this extensively. DER, let's classify DER, right? DER, you classify into two type of asset. I think we discussed in the morning too. One is controllable, one other is not controllable. If you are asking for a PV farm, change the shape like this. It's not possible because PV farm output is very constant. And if you change shape like this, it will be connected. So who will help to make a shape like this? Only the controllable asset, which are batteries. Right? So battery has two jobs. One job is to take care of PV, meaning PV changes, battery is absorbing this. Take care of that. And then extra will give you this set point shape from the battery. Now that control is not easy. You have to look at the state of charge of the battery. You have to maximize the capacity, given capacity of the battery, and do the two jobs. You have to look at in future what will be the change in the PV and then adjust the juice in the battery. Otherwise, after 10 minutes, battery will die out and you just bring it. So it's a little bit complex with respect to control is concerned. But only one device or active device that can do is energy storage. You cannot ask the photovoltaic to, you understand that? So now there was a question which you asked, what happens? Do you need energy storage for every group of photovoltaics? Well, ideally great. But what happens if I don't have? What happens if only two? Well, you put it in two locations, like I said, in the two parts in the feeder. Groups can still be there. Between the groups, I don't guarantee that there is no power transfer because I don't have energy storage in the group. But I can guarantee for the entire group, this energy storage will take care of the power balance. So that local duct, that area is satisfied. So now utility can say, well, yeah, I mean this is great, but I like to have a small energy. Yeah, that is you invest money, you will have a what do you call? You will have a sheet that says what is the benefit when and you decide to invest. It's up to you. You can invest. Make sense? That is the thing. Otherwise, obviously, you cannot do. So when we implemented the utility says all these things are great, but I can only invest in two energy storage maximum on feeder and two locations, and that location is decided by me, not you. Meaning, not we said yes, that's fine. That we put in the location and we'll do the control architecture and we'll see what benefit you get. You'll some benefit with control. Okay, so we did today talk about control framework. We talked about how the control framework is implemented. We talked about how you do node voltage control with the legacy control part. We talked about node voltage control with respect to time. Then we extended that into talked about the relation of active power with the node voltage control. Then we said, wow, how we do active power with voltage. We call it volt watt. And we said volt bar what? How do you do active power with voltage rate? And finally, we looked at a tool that can be implemented to do groups of this in a power distribution system. So that is something that we gain some knowledge on. So what we do now after the break is we come back and we do a tutorial. We will first do a which one do you want to do first? Power flow or you said both. So power flow, we can start on writing some small code and integrated power flow. And then we have one more hour in the afternoon. I think we will do OPF, optimal power flow 5-bus system using MATLAB. So that's basically our hands-on. What I will do is I will actually give that same problem as a take home, which means if you have not completed in 2 hours, and you can complete that for tomorrow. Tomorrow there will be I think an exam or a test which we wanted to do. So what we will do is towards the end while we do this 1 hour in the evening as a hand and then submitting tomorrow, I will review what we have done so far. For example, key factor. If you look at a power flow, what is the state variable? We talked about it. These are the kind of indicative questions that may come for tomorrow. So you can actually not exactly probably the same. So the state variables for the power flow is, what are the state variables when you solve a power flow? Voltage and angle of voltage are the state variables when you solve a power flow. This is also related to how much attentive you are. So you will actually see the benefit. But we'll go through some other things, we'll review some of the things which is probably helpful for you. Not necessarily for the test, but it's general knowledge gaining purpose. So we will probably reserve some 20 minutes or some to just go through some review so far what we have done. And then we have a lecture in the afternoon where we will talk about how do you implement this in real time with the OPF and control all in one loop. So we will talk about that. If you want to implement something in your lab or implement something in prototype in hardware integrated software prototype or some, we'll show you some our experience. We'll show you some ways that we implemented. We'll just focus on that. No more theory or no more result. But we talk about how to do that. So that's something which we will also do. So the rest of the today we'll focus on that. Good. All right. I think we'll stop.
Thank you, sir, for your insightful session. We have learned from a lot. Hope you all are enjoying the session. If anyone have query, then please ask. Okay, then we have break for a tea break. outside the seminar hall, and we are regathered after 15 minutes. Okay, thank you.